Yes, good morning.
Good morning, sir.
Good morning, sir.
Okay, we are discussing about the preparation properties and applications of polyvinyl chloride. Okay, the last class we discussed about the polyvinyl chloride. Today we'll discuss the nylon 6 and Teflon. Okay, in the last class we discussed about the polyvinyl chloride. Today we are going to discuss the preparation of properties and applications of nylon 6 and Teflon. The last one we have bakelite. With that, we have completed these preparations, and last one topic we have biodegradable polymers. With that, we'll complete the CA1 syllabus. Yeah, coming to the preparation of nylon 6. Involved in the preparation of polyvinyl chloride, PVC. Okay, vinyl chloride. Okay, what are the monomers? Monomers involved in the preparation of PVC. PVC is prepared by heating the vinyl chloride in presence of peroxide or hydrogen peroxide. Under pressure gives the polymer, that is polyvinyl chloride. Polyvinyl chloride. The monomer vinyl chloride is prepared by treating the acetylene with hydrochloric acid HCl at 60 to 80 degrees in presence of metal chloride, that is zinc chloride, as a catalyst gives the vinyl chloride. Okay, these are the properties. Now coming to the second preparation, that is nylon 6,6. Already in this condensation polymerization. Okay, it is prepared by addition polymerization. PVC is prepared by addition polymerization. Here it is prepared by nylon 6,6 condensation polymerization. Okay, here nylon belongs to polyamide class of synthetic polymers, which is having the repeated amide groups. Okay, it was first synthesized in the London, and the technology was taken and manufactured in the New York. After the two cities, okay, NY is nothing but New York, from the new and Y from the York, New York. Okay, nylon. Okay, NY stands for New York, and the LON in the nylon. Okay, NY stands for New York and LON stands for London. Nylon. Okay, LON from London, where it was synthesized. Okay, the polyamide was given the name nylon. Okay, the name nylon has been came from New York. Okay, New York, from New York is taken NY, and from London first three letters LON. Okay, nylon. Okay, New York and London. From New York is taken NY, and from London LON is taken first three letters, and the name which is came as nylon. S. Yeah. Okay, there are different types of nylons, like nylon 6,6, nylon 6,10. Okay, the first number 6 stands for, okay, here we have 6,6. What is the name this 6,6 indicates? The first number stands for number of carbon atoms. Okay, the nylon 6,6 first number stands for number of carbon in the diamine, and the second number indicates the number of carbons in diacid. Okay, in the preparation of Nylon 66. Okay, the first 6 stands for number of carbons in the diamine. Okay, hexamethylene diamine we are taking. Okay, there 6.
Sorry, your sound is lagging.
What happened? Is it all? Is clear or not clear?
Sir, it is lagging, sir.
Lagging. Okay. Okay, the first number stands for number of carbon atoms in the diamine, and the second number, second 6 in the 66, the second number stands for number of carbons in diacid. Like in the preparation of nylon 66, we are taken. Okay, what adipic acid? Adipic acid is CH2 taken. Okay, 4 times COOH. COOH. Okay, this is number of carbon atoms indicates the first number stands for number of carbons in the diamine. It is adipic acid, the monomer, adipic acid. Okay, this is the second number. Second number indicates the number of carbons in the diacid. Diacid is here 6 carbons. One, okay, here 4 carbons and one more here. This is indicates the 6. So the 6 in the nylon 6 came from this presence of these 6 carbons. One here 4 and here 1. So totally 6 carbons are present. Okay, second number indicates the number of carbons in the diacids. In the diacid we have 6 carbons, so here the number 6 indicates the diacid. And the first number is the hexamethylene diamine. Hexamethylene, the formula is hexamethylene diamine hexamethylene, CH2 taken 6 times and NH2 hexamethylene diamine tetraesteric acid. Okay, hexamethylene diamine. Here hexamethylene, here 6 carbons are there in the diamine. Okay, this is the first carbon. Okay, first 6 indicates this. Okay, number of carbons in the diamine. 6 carbons are there, so it is called nylon 66. Nylon 66. Coming to the preparation. Okay, preparation, it is prepared by condensation. Already I have said that it undergoes condensation polymerization.
The voice is getting stuck, sir.
Okay, wait a minute, I will change the network. Okay, now is it okay? Nylon 66 is prepared by condensation polymerization of hexamethylene diamine. Hexamethylene diamine is this one. Okay, the monomer hexamethylene diamine and another monomer is adipic acid we are taking. This is the monomer. These two monomers are undergoes condensation. Okay, by removal of water molecule here. Okay, H2O. 2H2O. The byproduct is 2H2O. It gives the product that is nylon 6,6. Okay, that is C double bond O. Okay, C double bond O, CH2 taken 4 times and C double bond O. And here it NH CH2 taken 6 times NH. Okay, like this is the polymer, indicates N plus 2H2O. Byproduct is H2O is a byproduct here. This is nothing but nylon 6,6. Nylon 6,6. Okay, it is prepared by condensation polymerization of hexamethylene diamine with adipic acid. Hexamethylene diamine with adipic acid gives the nylon 6,6. Nylon 6,6. Here coming to the properties. Okay, properties. It has high melting point. Okay, melting point. The range of melting point is 264 degrees centigrade. Okay, it has high melting point, and this the range is 264 degrees centigrade due to the hydrogen bonding between the hydrogen of amide groups. Okay, hydrogen of amide groups and oxygen of C double bond O group. Okay, the reason why the range the 264 is because the whatever the bond present between the amide groups, okay, NH bond, nitrogen and hydrogen bond is okay, is the reason for the high melting point of nylon 6,6, and it's also the oxygen, that is C double bond O group. Okay, and the nylon 6,6 have good strength. Okay, it has good strength. It absorbs a little moisture, and so it is a drip dry in nature, and the fibers are flexible and retain the original shape after the use. Okay, after the use it comes to this original shape after the use. Okay, the melting point of the nylon 6,6 is because of presence of hydrogen bonding between the amide groups. Okay, hydrogen of amide groups and the oxygen of carboxylic group. Okay, the range of melting point is very high, that is 264 degrees centigrade, and it has good strength. Good strength. It absorbs little moisture, and the fibers are flexible and retain its original shape after the use. It comes to its original shape after the use. And here nylon 6,6 possesses high temperature stability and good abrasion resistance. Okay, means the smoothness of the surface. Abrasion resistance is the good abrasion resistance. It has the nylon 6,6 possesses a high temperature stability and good abrasion resistance. They are insoluble in common organic solvents. They are insoluble in common organic solvents like benzene, acetone, and soluble in phenol and formic acid. They are soluble in phenol and formic acid. Insoluble in common organic solvents like benzene, acetone, and soluble in phenol and formic acid. Fibers are easily blend with wool to increase the strength and abrasion resistance of the wool. Fibers are undergoes blend with okay, means nothing but it undergoes mold with wool to increase the strength and abrasion resistance of the wool. Coming to the applications of this nylon 6,6. Okay, it is used for fibers. Okay, these are used as a fibers, means which find to use in making socks. Okay, making socks, hoses, and the dresses, carpets, etc. Undergarments and dresses and carpets, etc. It is also used for making filaments for ropes. Okay, for rope, preparation of ropes, making filaments, and the bristles for the toothbrushes. Okay, bristles are nothing but toothbrushes, whatever the plastic. Okay, the fibers that are made up of these are bristles. We call it as bristles, and the tire cards. Tire cards also made up of this nylon 6,6. Okay, it is used in making socks, and the hoses are nothing but whatever the shoes is in shoes inside the one hoses are present. That is, we call it as hoses, and the dresses and carpets, etc. in making filaments for the ropes, bristles for toothbrushes, and tire cards. Okay, next the second preparation, the third preparation, that is Teflon. Teflon, another name of Teflon is polytetrafluoroethylene. Okay, Teflon, another name is polytetrafluoroethylene. Polytetrafluoroethylene is nothing but Teflon. Polytetrafluoroethylene is nothing but Teflon. It is called as Teflon. Okay, how we are going to prepare? How we are going to prepare this polytetrafluoroethylene? Polytetrafluoroethylene. Okay, Teflon is obtained by polymerization of on ethylene molecule. If you replace the CH2 double bond CH2, if you replace this hydrogen with fluorine, you will get the tetrafluoroethylene. Okay, here Teflon is obtained by polymerization of tetrafluoroethylene. Okay, we called it as, here in the place of, if you replace this with fluorine, you will get CF2 double bond CF2. Okay, ethylene becomes tetrafluoroethylene. Tetrafluoroethylene. This is a monomer we are using in the preparation of TFE, that is polytetrafluoroethylene. Polytetrafluoroethylene. Okay, ethylene in presence of fluorine gives tetrafluoroethylene. Okay, here it is obtained by Teflon is obtained by polymerization of tetrafluoroethylene. This is the monomer. Okay, on polymerization in presence of benzyl peroxide as a catalyst, it gives the polytetrafluoroethylene. Polytetrafluoroethylene. This is a monomer on polymerization gives polytetrafluoroethylene. Teflon is obtained by polymerization of tetrafluoroethylene in presence of benzyl peroxide as a catalyst. Okay, how we are going to prepare this tetrafluoroethylene is, okay, this tetrafluoroethylene is prepared by, okay, from ethylene. Ethylene means CH2 double bond CH2 in presence of fluorine, it gives tetrafluoroethylene. Tetrafluoroethylene. Okay, tetrafluoroethylene in presence of polymerization of tetrafluoroethylene in presence of benzyl peroxide gives, okay, benzyl peroxide acts as a catalyst. Okay, gives the polytetrafluoroethylene. Okay, F2C single bond CF2. Okay, gives the PTFE. PTFE, another name for PTFE is Teflon. Okay, tetrafluoroethylene or Teflon. Teflon is obtained by polymerization of tetrafluoroethylene. Tetrafluoroethylene on polymerization gives, in presence of benzyl peroxide as a catalyst, gives Teflon, nothing but polytetrafluoroethylene. Polytetrafluoroethylene. Coming to the properties of this polymer PTFE, okay, polytetrafluoroethylene. Okay, due to the presence of high electronegative fluorine atoms, okay, it has fluorine atoms. Here CF2 double bond CF2, that is, it is a monomer. Monomer in presence of benzyl peroxide as a catalyst gives the CF to single bond CF. Okay, so CF2 single bond CF2. Okay, this is the indicates N, means polymer. Monomer, it is tetrafluoroethylene. Monomer is tetrafluoroethylene. The presence of benzyl peroxide as a catalyst gives the polymer, that is Teflon. Okay, polytetrafluoroethylene. Polytetrafluoroethylene or Teflon. Polytetrafluoroethylene or Teflon. Okay. Coming to the properties, due to the presence of high electronegative fluorine atoms, results in the very strong attractive forces between the different chains. Different chains. Okay. Presence of high electronegative fluorine atoms results in the very strong attractive forces between different chains. Okay. These strong attractive forces give the material extreme toughness. Use the extreme toughness and high melting point. High melting point. Okay, due to the presence of these fluorine atoms, okay, there are strong attractive forces between different chains. Okay, this strong attractive forces gives the material extreme toughness and high melting point above 350 degrees centigrade. Okay, exceptionally high chemical resistance towards the all chemicals. Okay, high chemical resistance towards all chemicals except alkali, okay, and hot fluorine. Except exceptionally high chemical resistance towards all the chemicals, but the exception for this is okay, alkali, metal, and hot fluorine. Okay, and here the density of this polymer, okay, Teflon is 2.1 to 2.1 to 2.3 grams per cc cubic centimeter. Okay, it has high density, that is 2.1 to 2.3 grams per cubic centimeter, and it is a very strong hard polymer, very strong and hard polymer that can be machined or drilling in punching, etc. Okay, here because it is a strong and hard polymer, we can do for this we need to do the drilling and punching, etc. It acts as a very good electrical insulator, means it does not allow the electric current to pass through it. It poses very good abrasion resistance. Abrasion resistance is smoothness on the polymer. Okay, smoothness present on the polymer is nothing but good abrasion resistance. It is poses very good abrasion resistance. Okay, next, coming to the applications. Okay, the applications of the Teflon is, it is a Teflon is a very good insulating material. Okay, very good insulating material for motors, transformers, cable wires, etc. Cables, wires, etc. The Teflon is a very good insulating material for motors, transformers, cables, wires, etc. And it is used in making gaskets. Gaskets are nothing but in the pressure cookers, whatever the rubber that is present is nothing but a gasket. Okay, pressure cookers. Okay, whatever the rubbers we kept to maintain the okay, the rubber that is nothing but the gasket, making the, it is made up of Teflon. Okay, it is used in making gaskets, pump parts, okay, and the tank linings, tubing, etc. In tubing, etc. It is having the extreme chemical resistance, and it is used for making chemical carry pipes, making chemical carry pipes, and non-stick stopcock for burettes. Okay, for preparation of burettes. Okay, here cock for the non-stick stopcock for the burettes and non-stick cookware products. Example, pans. Okay, okay, pans are non-stick cookware products like pans. Okay, in the burettes also, the preparation of burettes also the Teflon is used, and in the preparation of non-stick wares like cookwares products like pans are prepared by this Teflon. Okay, here in Teflon, uses of Teflon in the preparation of rubbers, tires. It is a good, very good insulating material for motors, transformers, cables, wires, etc. It is used in making gaskets, pump parts, okay, tank linings, tubing, etc. Due to the extreme chemical resistance, it is used for making chemical carry pipes, and non-stick stopcock for burettes. For burettes, in the burettes also we'll use this Teflon, and the non-stick cookware like pans. Pans are made up of non-stick ware, that is we use the Teflon material over there. Okay, here the last preparation that is bakelite. Okay, last preparation, that is the preparation of bakelite. Nothing but it is a phenolic resin. Okay, phenolic resin we call, another name is phenol formaldehyde resin. Okay, bakelite, all these are common names. Bakelite is nothing but phenolic resin or phenol formaldehyde resin. Okay, now coming to the preparation, how we are going to prepare this bakelite. Okay, fourth preparation, we have the first one is PVC, second one is okay, Second, we have prepared nylon 66 and Teflon. Okay, this is the fourth preparation is Bakelite. Okay, how we are going to prepare this Bakelite? Okay, Bakelite is important thermosetting resin, thermosetting resin named after the scientist Bakelite. Okay, in the very first classes we have discussed that the scientist Leo Bakelite. Okay, the name has been came from the scientist Bakelite. Okay, Bakelite is a important thermosetting resin named after the scientist Bakelite, who synthesized this resin in the year 1909. Okay, in the year 1909, he prepared the thermosetting resin. Okay, and the name has been came from the scientist. His name only, that is Bakelite. Okay, Bakelite is the name came from the Bakelite. Okay, it is prepared by condensing the phenol with formaldehyde in the presence of acid or alkaline as the catalyst. Alkaline is nothing but base. Okay, it is prepared by condensation of phenol and formaldehyde. Phenol is nothing but on the benzene ring, if OH is present, that is phenol, and the formaldehyde is okay HCHO, that is formaldehyde. Okay, on condensing these two monomers, okay, phenol and formaldehyde, you will get the Bakelite. Okay, in the presence of what? In the presence of acid H plus or OH minus. H plus or OH minus, you will get the phenol phenol formaldehyde. We call it as Bakelite. Okay, it is prepared by condensation of phenol with formaldehyde in presence of acid or alkali as a catalyst. The Bakelite is a commercial name for the polymer is obtained by polymerization of phenol and formaldehyde. Okay, phenol formula is on the benzene, if OH is present, we call it as phenol, and the formaldehyde HCHO. HCHO is the formula for formaldehyde. Formaldehyde, acetaldehyde, it will replace the H with CH3, that we call it as acetaldehyde, C2H5. Okay. Here, the initial reaction result in the formation of ortho and para-hydroxy methylyl phenol. Okay, methylyl phenol, which reacts with to form the linear polymer. We call it as novalic resin. Okay, it gives the novalic. See, we have the steps involved. There are 3 steps involved in the preparation of this phenol. First, what happens means the step 1, step 2, and step 3. We have 3 steps, and this is the conversion of the novalic to Bakelite. The step 3. We'll discuss one by one. Coming to the preparation, phenol is made to react with formaldehyde. Here we are taking the phenol on the benzene, if OH is present, in the presence of formaldehyde HCHO. Okay, in the presence of alkali or acid to produce non-polymeric mono, di and trimethylyl phenols. Okay, here we got, this is a monomethylyl phenol. Same, this methylyl phenol in the presence of formaldehyde, we got dimethylyl phenol. Okay, again in the presence of formaldehyde, it gives trimethylyl phenol. Okay, well, the step 1 is what? Okay, here the conversion of phenol. Okay, phenol reacts with formaldehyde in presence of what? In presence of acid or alkali, it produces non-polymeric mono, dry and trimethylyl phenols. Okay, depending upon the phenol formaldehyde ratio, okay, we got mono, di and trimethylyl phenols. Mono, dry and trimethylyl phenols. Now, what we need to do means, now we need to react this monomethylyl with another mole of monomethylyl phenol. You will get the linear chain of novalic resin by elimination of H2O molecule. Now in the step 2, here now whatever we got monomethyl, we are taking one monomethyl. Okay, same like that. If you take dimethyl, you will get the novalic resin. Trimethyl also. I am taking whatever we got monomethyl. Now this monomethyl phenol reacts with another monomethyl phenol. Okay, by elimination of water molecule, it gives a linear novalic resin. Linear novalic resin. This is the novalic. How we are going to prepare this means I am taking one monomethyl phenol. Monomethyl phenol is CHO. Okay, here OH is present. To this, if CH2OH is present, it is called as monomethyl phenol. Monomethyl phenol. If you react this with another mole of monomethyl phenol. Monomethyl phenol, OH is present again here. Here, whatever the hydrogen is present, by elimination of this H2O molecule, okay, 2 moles of monomethyl phenol by elimination of H2O, it produces the novalic resin, linear polymer, that is the novalic. Okay, the same thing. If you represent here, you will get the novalic resin. Novalic is the whatever the novalic we got. Okay, when novalic resin is further heated in presence of formaldehyde. Okay, further heated in presence of formaldehyde and hexamethylene tetramine are added to this. If you add, it reacts with formaldehyde and hexamethylene tetramine are added, which converts the soluble and fusible novalic. Okay, this whatever this is a soluble form. Novalic resin is the soluble and fusible form. Okay, soluble and fusible form. This is soluble in nature. Novalic linear polymer resin. Okay, this soluble and fusible form when reacts with formaldehyde and hexamethylene tetramine are added, which converts the soluble fusible novalic into the hard infusible and insoluble polymer. Okay, insoluble cross-linked structure, that is the bakelite. Okay, this is the bakelite structure. We'll see one by one, step by step. First, what we are going to do, there are 3 steps involved in the preparation of bakelite. First, what we are going to do means, okay, here I'm writing here. Here, the step 1 is, okay, the 3 steps are involved in the preparation of bakelite. Step 1 is here phenol reacts with okay, formaldehyde in the presence of H plus or OH minus. Okay, acid or base alkaline we are taking. It forms monomethyl phenol. Okay, it forms monomethyl phenol, CH2OH. CH2OH. Again, if you react H2O, it forms dimethyl phenol. Okay, we want this one. Okay, monomethyl phenol. The name of this compound is monomethyl phenol. Okay, this monomethyl phenol reacts with, okay, monomethyl phenol reacts with another mole of monomethyl phenol. Step 2, what happens means, okay, monomethyl phenol, okay, CH2OH, it reacts with another mole of monomethyl phenol, another mole of monomethyl phenol. Okay, this is another mole of monomethyl phenol or orthohydroxy, whatever we here the OH is present to the, this is a functional group, the OH is present, we call it orthopara. It forms, okay, novalic resin. Novalic is the, okay, if you remove here from hydrogen, you will get the novalic resin. The novalic is a linear form, linear and the fusible soluble form. Okay, this novalic in the presence of Okay, this in the presence of what? If you react this novalic in the uh, formaldehyde and hexamethyl hexamethylene tetramine. Okay. Novalic resin, if further treated in presence of formaldehyde and hexamethylene tetramine is added to that novalic. What happens means it converts the soluble and fusible novalic into hard, infusible, insoluble solid of cross-linked structure. Okay, cross-linked structure that is nothing but bakelite. Okay, this bakelite is the hard, infusible, and insoluble solid of cross-linked okay structure of cross-linked structure called as bakelite. See the step 1, there are 3 steps. This phenol reacts with formaldehyde. Okay, phenol reacts with formaldehyde in the presence of, already I have said, in presence of acid or base, acid H plus or base, whatever we need to take, it gives ortho, okay, monomethyl or ortho, we call it as in the IUPAC name, ortho or para-hydroxy methyl phenols. Okay, this is the intermediate one. Now, this on polymerization. Okay, polymerization means we are taking another mole of here. The step 2. Step 2 is now orthohydroxy. In the IUPAC name we are calling. Okay, the same thing we call it as monomethyl. Both are same, monomethyl. In the IUPAC we are calling ortho. Okay, to this the functional group CH2OH. The OH is present to ortho to this position. We call it as orthohydroxymethyl phenol. Orthohydroxymethyl phenol is a IUPAC name. IUPAC name, common name is monomethyl phenol. Monomethyl phenol is the common name, and the IUPAC name is orthohydroxymethyl phenol. Orthohydroxymethyl phenol, para-hydroxymethyl phenol, that we got as the intermediate. Okay, to this orthohydroxy I am taking, ortho or para, whatever you need to take. Okay, orthohydroxy I am taking, orthohydroxymethyl phenol on polymerization. Polymerization means we are reacting another mole. Okay, another, what it happens, it gives by elimination of water molecule. By elimination of water molecule, we got the novalic resin. This is the novalic resin. Soluble fusible form of resin is novalic, linear polymer. This is the linear polymer. By elimination of H2O, we got this. Okay, by elimination of H2O. Now to this, I am heating in the presence of what? Heating this novalic on heating in presence of formaldehyde and hexamethylene diamine. Hexamethylene, okay, heated in the presence of formaldehyde and hexamethylene diamine. Hexamethylene diamine, what happens? It gives the cross-linked polymer. Okay, cross-linked, insoluble, infusible, and cross-linked polymer, that is nothing but novalic. Okay, nothing but bakelite, cross-linked polymer. Okay, this in the presence of novalic linear polymer, in presence of formaldehyde and hexamethylene diamine. Hexamethylene diamine, it gives the polymer, that is bakelite. Okay, which is a cross-linked polymer, cross-linked infusible, insoluble form of polymer, that is bakelite. Okay, bakelite is a cross-linked polymer. Here the same thing, novalic OH is present. Okay, this is a polymer. We got it is bakelite. This is important. Preparation, properties and application of bakelite is important. Okay, it has 3 steps. First step is the phenol reacts with formaldehyde in presence of base, acid or base. It gives the ortho or para-hydroxy methyl phenol, that is intermediate. This on polymerization by elimination of H2O, it gives the novalic resin, which is a linear fusible form of resin, that is novalic resin, linear polymer. This linear polymer reacts with in the presence of heating, okay, this novalic is heated in the presence of formaldehyde and hexamethylene diamine, it gives the bakelite. Bakelite, that is cross-linked polymer, infusible, insoluble, cross-linked polymer, that is the bakelite. Infusible, insoluble, cross-linked polymer, that is bakelite. Now coming to the properties of this bakelite. Okay, bakelite is hard, rigid, strong polymer. Okay, hard, rigid, and strong polymer. It is a water resistance polymer. Water resistance polymer. It has a good chemical resistance, and resistance to acids, salts, many organic solvents. But it is attacked by alkalis. Alkali is nothing but base due to the presence of OH group. Okay, it is good chemical resistance, and it is resistance to acids, but it is not resistance. It is easily attacked by bases OH minus. Okay, salts and many organic solvents, but it is attacked by alkalis OH due to the presence of OH group. It is easily attacked by alkalis. Why? Because in the intermediate that the OH is present, so it is easily attacked by the OH group present in the base. So it is good resistance to alkali acids. Okay, resistance to acids, but easily attacked by the base due to the presence of OH group in the bakelite. Presence of OH group in the bakelite it is easily attacked by the alkalis base. It is used for water purification by ion exchange process in the boilers. Okay, this bakelite is used as a purification process in the ion exchange process in the boilers. It is an excellent electrical insulator. Insulator which does not allow the electric current to pass through them. So it acts as an excellent electrical insulator, and it is a very good corrosion resistance. Okay, means it does not undergo any corrosion. It is resistance to corrosion, very good corrosion resistance, and it is resistance to oxygen, carbon dioxide, moisture, light, and UV radiations. Very good corrosion resistance. The resistance to oxygen, carbon dioxide, moisture, UV radiation. Okay. Now, next coming to the applications. It is used for making electrical insulators. Okay, insulator parts like switches, switchboards, plugs, switchboards, etc. Okay, all these are made up of this polymer bakelite. Okay, and for the making molded articles. Okay, in the telephone cabinets, telephone parts, cabinets of radios, and television cabinets, whatever the cabinets that are present in the television, that is cabinets are nothing but whatever the part, plastic part we call it as, that is made up of this bakelite only. And it is an ion exchanger in water purification by ion exchange method in boilers. It acts as a ion exchanger, means it acts as a resin, ion exchange resin in the purification of ion exchange method in the boilers, in the paints, okay, and varnishes also. We will use this bakelite for making bearings used in the propeller shafts, in the paper industry and rolling mills, all. Okay, in the paper industry also we will use this as making bearings, for making of bearings using the propeller shafts, paper industry and rolling mills, all. In this we will use this bakelite. For making wood laminates and glass laminates, we use this bakelite. Okay, wood laminates and glass laminates, we use this bakelite. Okay, bakelite is prepared by phenol in presence of formaldehyde, acid, or the base, that is OH, used as a catalyst. It gives the ortho or para hydroxymethylphenol. Okay, when this ortho hydroxymethylphenol on polymerization, okay, it gives the, by elimination of H2O, it gives a novalic resin, which is a linear polymer, fusible polymer, fusible novalic resin. This novalic resin, in the presence of heated in the presence of formaldehyde and hexamethylene diamine, it gives the polymer, that is the cross-linked polymer bakelite. Cross-linked polymer, that is bakelite. Okay, here the benzene, if OH is present, OH CH2, CH is a polymer, and this again OH CH2. Okay, here again same thing, CH2 OH. Okay, here down OH CH2. This benzene, here OH CH2. Okay, this we call it as the bakelite. CH2 benzene, CH2. Okay. Yeah, you have any doubts, ma?
Sir,
Preparation. Yeah. Tell me, ma.
not
Yes.
about the current topic, but exactly until where do we have CI?
When you have CI, you are asking.
Till
No,
where,
sir.
sir?
Ante
Till where?
a topic varaku exactly.
This is the up to here. It is there, ma. Last we have biodegradable polymers. I will complete on Monday. Okay, up to there we have syllabus for CIE.
So this is all a part of introduction to polymers, sir.
Yeah. This is just introduction. Introduction means we have in the module 3 half of the part.
Okay, sir.
Like
can you-
this, you will get as a you can if you can study or you can leave it as a choice, because already you got the question paper pattern yesterday, right?
Yes, sir.
Okay, you have 5 questions, ma. Out of 5, you need to answer 4. The 5th question is from the module 5, module 3. Sorry. Okay.
Yes, sir.
Sir,
Okay.
can you once screen share the question bank and show what all questions would be coming from this module?
Yeah. I will share you now. Wait a minute. Question bank. Yeah, ma, this is a question bank I'm sharing you. Is it visible, ma?
Yes, sir.
Yes, sir.
From part A, you tell, sir, what all questions.
Yeah.
Till
From the
where?
module 3, you're asking, or you're asking from every module? I think.
No, sir. Only
Module
module 3.
3.
Module 3. Okay. See, this is a module 3, ma. Part A. Okay, these are the short answer you won't get. Okay. You directly go to the part B. Okay, these long answers are there. No,
Short
from this
answers
you will
won't
get it.
get, sir.
No, you won't get, because the pattern is already you got the pattern, right? Okay, if you read this part B also, the same you have in the part A. Okay, whatever we have in the part B, the same it will be repeat, ma. See, this is the what are the one red mark line will be there. Yeah, whatever this line is there, no, ma. This blue color one, 10 up to 10 questions we have for the CI one.
Okay, sir.
Okay, this 10 up to 10 is there in the part B, up to 10 is there, no? Up to here you need to, we have the last topic, biodegradable polymers. Yeah, everything we have completed. See, you have any doubts you can ask. Okay, different types of polymers already we have discussed. We have 3 types. One is, I will discuss the paper also, ma. In the one class I will discuss. Okay, thermoplastic resin, thermosetting resins, differences, comparison. What is meant by compounding of plastics? What are the ingredients used in the compounding? That is resins, plastics, the fillers. Okay. Briefly about explain briefly about thermoplastic and thermosettings with example. Okay, you need to give the example here. What are thermoplastic resin and what is thermosetting resins? Here, preparation, properties and applications of this phenol formaldehyde. Whatever we discussed now, no. that is phenol formaldehyde. He is asking in indirect way. Okay, here direct question is bakelite. Okay, he is asking in the form of preparation, properties, and engineering applications. Okay, preparation is how we are going to prepare it. It involves 3 steps. Okay, what are the steps involved? Okay, first one is step 1 is phenol reacts with formaldehyde in the presence of OH or acid. It gives the orthohydroxymethylphenol. This orthohydroxymethylphenol on polymerization, the step 2, you will get the novalic resin. Okay, which is a linear polymer, fusible soluble form. Okay, this fusible soluble form in presence of heated in the presence of formaldehyde and hexamethylene diamine, you will get the phenol formaldehyde. Phenol formaldehyde, we call it as bakelite. Okay, same thing. Now, here the question 6 is asking synthesis, properties, applications of nylon 66. Nylon 66 already we have. Okay, and Teflon. Same. In the 7th question is asking Teflon and bakelite. Okay, Teflon and bakelite. In the 8th question is asking in a different way. Polytetrafluoroethylene. Polytetrafluoroethylene is nothing but Teflon only. Okay, is asking PVC. PVC in the form of polyvinyl chloride. Polyvinyl chloride. It is nothing but PVC. Teflon. Polytetrafluoroethylene. Another name is Teflon. Okay, it is asking in a different way. Here he is asking directly Teflon and bakelite. Teflon name is polytetrafluoroethylene, and the bakelite is phenol formaldehyde. Another name for bakelite is phenol formaldehyde resin. Okay, and here same preparation, properties, and applications of bakelite. 9th question. Okay, last we have this biodegradable polymers. We'll discuss this 10th question in the next
Sir,
class.
part C also, sir.
Part C also. Okay, right.
Sir, and do you have the notes for this chapter?
Yeah, I will share.
Yes, sir. Please share, sir.
I will share. Sure.
Thank you,
Okay. Okay. In the next class, we'll discuss more. Yes. In the next class, I will discuss this part C.
So, like, just tell till where.
Yeah. I will tell you. No problem. Here also one line will be there, ma. Determining. No, it is 4 point. It's not there. I will tell you. Glass sizes used in the molding. Thiol rubber can be vulcanized. No, it is not there. Teflon is highly chemical resistant. Nasal rubber needs vulcanization. The 4th question is there, no? Up to 4th question. Rubber, no, it is rubber becomes stiff and stretching. Some questions are there. Okay, first is there, ma. First PVC, second is there. Third rubber, it is not there. 4th is there. 5th one nasal rubber. Now rubber, it is not there in our syllabus. Means it is there, but the second next CAE2 you will get this nasal rubber, and the 5th one nasal rubber also it vulcanization is next we are going to discuss in CAE2. Thiol rubber, it is also not there. No? Plasticizers. Okay, plasticizers we have this plasticizers used in the during molding of plastics. Okay, what is the use of this plasticizers? Okay, it gives the plasticity and flexibility of the polymer. What are the functions of lubricants? It is not there. Okay, this is in the next flash point. It is also not there. Flash point and fire point. And what is the significance? Now coming to what are the questions you have means.
1 to
7th one is there, ma. 7th one, 4th one, 2nd and 1st.
4 questions.
4 questions.
Okay.
These are okay. These we have in this CAE1. Remaining you will get it in the CAE2. Okay.
Please share the lecture notes.
I will share
Okay,
it. Okay. Already I have sent the module 1 and module 2.
Yes, sir. Yes,
I will send this for module 3 also. Okay.
Okay. Thank you, sir.
Okay. Welcome. Okay. I'm stop sharing, ma. Thank you, one and all.
Thank you, sir. Have a nice day.
Thank you, sir.